Greetings, everybody. Thank you for joining us today. This is Timur, and welcome to our webinar on advanced topics with exabyte.io. Today, we're going to be speaking about a few things. And before we start, let me go through some important concepts. The goal of this seminar is to help users understand what exabyte.io platform is and how to work with it, how to benefit from using it. This is the second webinar in a monthly recurring series. First Friday of the month, we speak about getting started. Third Friday, we speak about advanced topics. And here is where we are at now. Every participant should be a registered user of the Exabyte platform, and every participant will receive this presentation in a PDF format after the webinar. The webinar is recorded and will be made available to you. Much of the information is still available at docs.exabyte.io as well. One moment. If you have any questions at any point in time, you can ask those via webinar chat. I hope this functionality is already familiar to you. In Zoom window, we have this chat option and Q&A option. You can use either one, and we will go through the questions at specific designated times during this webinar. I see one attendee raised their hand. Is that an urgent question? If it is, please ask inside the Q&A. If it's not, let's wait until the Q&A session to discuss it. Right. The user, we assume that the user is an experienced computational material scientist, familiar with tools like Quantum Espresso, VASP, and similar. We assume that the user understands the basics of Linux and Unix operating systems and has an established set of scripts and input files to perform the calculations. And the user would like to know that how these scripts can be migrated to exabyte.io and how to work collaboratively with other scientists online to see what their scripts, what they produce, and what calculations they run. And in order to do that, there are two options. First option is to bypass the web interface and use alternative connection options to access command line environment and use existing scripts. The good side of this first option is it's very quick and familiar to many. And the downside is that it's error prone. It's difficult to reuse and share. Everybody has their own concepts that they put into the scripts. And for every single calculation, we have to adjust the scripts to be able to get the material information. In the second scenario, we adopt the exabyte.io platform approach, and we create material entities, the workflow entities, and using those two, we create the job for simulation. And this approach requires some time to learn. That's the downside. But it makes the logic for simulations to be reusable for multiple materials. It's easier to review what happened, and it's easier to collaborate. So for collaboration, we have exactly the same two options. Either users can bypass the web interface and collaborate using the shared file system. And this is, again, quick to start, but it is error prone. Or our platform users can adopt the Exabyte platform approach and then create material, workflow, and job entities and collaborate and edit those entities together with other account users and share them even publicly on the web, similar to this digital object identifier for publications. This will require some time to learn, but it is intuitive, it is easy to use, and it minimizes the errors from the user side. So here is the agenda that we're going to be following today. We'll speak first about the platform infrastructure, alternative connection methods, login node, file system, and shared access to data. And then we'll go through the entities like materials, simulation workflows, and calculation jobs in more details and explain how we can migrate an input structure from pw.x input to the platform, and so the same for the workflow logic. And we will finish with the overview of the collaboration in our platform. All webinar participants can request access to the webinar account, and this account has advanced features enabled for it, such as command line access, and users can see how the collaboration really works between the seminar participants. To save time, we'll be looking at the recorded videos of the functionality, but you can follow the presentation and use this webinar account to reproduce all the videos. So let's talk first about the platform infrastructure. And here is how it looks like. And this is the picture of the platform infrastructure. This is how it looks like from the engineering standpoint. And as you can see, there are multiple components, but the important ones are the computational clusters and the web interface and the data stack in between them. So if you look closer to the connection methods, we'll see that there are multiple. And we're going to be speaking about 3 of them in particular: the secure shell method, going straight to the command line login node, and 2 alternative connection methods coming from web interface to the login node again, the remote desktop, and the web terminal. There are a total of 4 alternative connection methods. So besides the web interface, our users can use a secure shell connection, a web-based command line terminal, remote desktop connection through a web browser, and the RESTful API. And today we'll be speaking about 3, and we'll omit the discussion of RESTful API for now. How can we enable the secure shell connection? To do that, we need to upload the public SSH key into the platform interface and make sure that it is lit up as green, so it is uploaded to the infrastructure. And then we can use any secure shell terminal to connect to the login node. The same is true for the web terminal. We can use the web terminal to connect to the login node, and we can do that directly from the web interface through the existing user session. This is how it looks like. We have to click on the user, and then click on the terminal, and right in the web browser, we have the command line connection. Remote desktop is also executed and realized through an equivalent web-based connection. Just like with the terminal, we can click on the remote desktop option instead, and we are presented with the familiar desktop environment. You can exit it by clicking on this cross in the top right corner. Now, to be able to use any of these remote connection methods, we first have to understand the file system on the login node that we're going to be connecting into, and understand that it provides access to multiple computational clusters. We did this on purpose to realize access to multiple different computational environments that include multiple different cloud providers. So, for example, cluster 001 in production right now is hosted on Amazon Web Services, and cluster 007 that we have in production today is hosted on Microsoft Azure. And the login node has access to the data on all of the masters connected. For the user's convenience, we share it through network and make it available in one command line folder to the user or to the organization. All 3 connection methods ultimately lead to login node, and then through it, you can access files on multiple different computational systems. So once we connect to the login node, we can see the user home directory first for each user, and it contains links to the computational clusters. So cluster 001 is a link to the file system on that cluster, and accordingly for cluster 007. So when we go and navigate into cluster 001, we have another set of system folders. Each of them represent a particular concept in the way that we organize the data. For example, exabyte.io represents a link to the organizational accounts folder in the file system, where the user is a member. I'm a member of exabyte.io account, and that's why I see this link here, a link to the data that we produce under this account. Then data folder contains the job data that is originated on the web applications. So in web applications, we mark each calculation with a certain identifier, and based on that identifier and the job name, we create folders inside this data folder. Links to the Dropbox folder that is shared between multiple parts of the infrastructure, and also templates for command line job scripts are the other two folders. So if you look at the infrastructure once more, we can notice that there is a Dropbox folder that is connected to pretty much every other part of the infrastructure. And what we use it for is similar in concept to the Dropbox well-known application company. It is used to share data between all these different parts of the infrastructure, and it has to be small data. We on purpose limit the amount available, the amount of storage available to 1 gigabyte. So it should either be scripts like Python scripts or set of potential files, for example, for the C functional theory calculations, small but very important parts of the data infrastructure that needs to be present on master nodes and computational nodes at the runtime. Inside the data folder, we have the jobs, the simulation jobs organized in a certain way. So if you go and navigate into the user's data folder, and we'd like to find a job originating from, for user Steven, from the project name default, and the job that is named new job November 11, 2018, with a certain ID in a database. We'll see that all of this are concatenated to create the final job name. So when we see a job with all these parameters in the user interface, that's where we're going to find it in the command line. An equivalent concept we also deploy for organizational accounts, except for their data is first hosted at the inside the shared directory. So for each of the organizational accounts, we have clusters that are one shared groups account name. So exabyte-io would go here in my case. Now, why it is important to understand the command line specifics? It's important to do that to understand it because there's certain functionality that we don't quite support yet on the web application, but you can still use remote desktop to access this functionality. And here is an example. I'm using xkristen to visualize the Fermi surface from the calculation that I performed on exabyte.io platform earlier. And by knowing how to find this pw.x file that is produced during the calculation, I'm able to use the remote desktop connection to visualize and analyze the data. Okay. All right. So here's a quick summary about the remote connection methods. Remote connection is an alternative way to access the exabyte platform. Instead of using a web interface, we can enable remote connection upon request. It is accessible to certain kinds of service levels, usually paid service levels, but we can also give this capability for novice users to try upon request. There are three options, web terminal, remote desktop, and both of these are in browser, inside the web browser, and a secure shell session. Remote sessions are connected to the login node with a separate home folder for each user. Home folder has links to directories for compute clusters. And the important note here is that command line jobs must be submitted from within a cluster directory. So we have to navigate first to one of the cluster directories before we can submit the command line job, because that's how we know which cloud provider or which part of the computational infrastructure to send these calculations into. There is a variety of software packages and an analysis software that is available through command line modules. Okay, let's see if you have any questions as of right now. I do have one hand raised, but let me try and cover the rest of this functionality, and then we can open up the discussion. Otherwise, if it's an urgent question, please ask it inside the chat or inside Q&A. all right? Okay, so now let's go ahead and speak about materials and how we can take the information from the example input files for Quantum Espresso and create material entity inside the platform. So here is an example workflow that I took from one of the platform users, where they attempted to calculate the band structure or the electronic structure of a particular material. Calcium, tungsten, and oxygen. So these are the three elements contained inside this material. And here are the input files for the SCF, the self-consistent field calculation, and the NSCF, non-self-consistent field calculation for this material, right? Now, how do we go about creating a material entity inside the exabyte platform? First of all, we need to examine the structural information that we have inside the input files. It's equivalent between the two. And we see that there are lattice parameters that are measured in the units of a lat, which means that this would be multiplied by the dimension of the cell. And the cell dimension is also given in atomic units, so in bores instead of angstrom. And then there are coordinates of each of the atoms given in crystal coordinates. So now then I go to the list of materials inside my account, and I've executed all of this under the webinar account. So you can reproduce and see these materials when you're looking into it. And I click on the plus button, and it opens up this materials designer session. And then I prepare the session by cloning the default material. Default material from this account is silicon FCC. I don't need to modify it. That's why I'd like to clone it, create a hot copy of this, which is not associated with any database entry. The silicon FCC already exists in the database. And if I modify it directly, it will be updated in the database, which I don't want. I want to create a new material. That's why I copy the default material and delete the original one from this current materials designer session. All right, and then I prepare its name. The next step is to set up the parameters for the crystal lattice. And just as I discussed it before, we set up the lattice as triclinic. That's to transfer the information from the SCF input file. And then we set up the parameters for the lattice in angstroms. So I convert the bores to angstroms in the cell dimension and set up the lattice A and B parameters accordingly. And then the parameter C is the parameter A multiplied by the value that I just extracted from the input file. Okay, and then all the angles, as we can see inside the input file, are 90 degrees. So that's how I set up the lattice parameters, by copying and setting up the lattice inside this form, right? And then clicking apply edits. The next step, as we can see here in the 3D visualizer, the cell dimensions are already present according to what we have in the original input file. The next step is to copy the crystal basis information. And for that, I can just copy and paste the corresponding lines from the Quantum Espresso input file. Here we go. We can see that now we have the correct atoms present inside this crystal lattice. And it does indeed look like a material that we wanted in the beginning. And the final step here is to select any kind of metadata, so attach any kind of metadata that we would like to this material. I'm using a tag from pw.x and creating a tag for this material, and then saving it in the database. So as we will see, after this loader done spinning, this material is now created in my database in the collection that belongs to this webinar account. And at the top of this collection, now we see this entry with the corresponding metadata. That's how we create a material from pw.x information. The second option, and that's what we support for POSCAR and CIF formats today, is to upload the structural information directly. And what we could do with the quantum espresso input, for example, we could go online to this site that can convert the quantum espresso input file to WASP or CIF input, and then use this input directly to upload it into the platform. I demonstrated how to do that in one of the previous webinars that was focused on getting started, and you can find one of these videos inside our YouTube channel. So after we have created the material, we need to go ahead and proceed with the creation of the logic that executes a simulation, right? The logic that executes a simulation is independent, usually, of the material. Sometimes there are certain parameters that we have to adjust based on materials, the material structure, but the actual structure parameters do not modify the logic. The logic includes self-consistent field calculation and then non-self-consistent field calculation. So it's relatively straightforward for this example use case. Now, how do I transfer this logic to the exabyte platform? Just like with materials, I need to start with opening up the materials designer session. And here is how we can do that. We go online, go to the list of workflows for the account, and click on the plus button. And that opens up an empty materials designer session. Sorry, workflow designer session. So in the workflow designer, I need to adjust the name of the workflow to be able to find it in the future, and adjust the name of the sub workflow. So here I have one sub workflow, which at present corresponds to quantum espresso as I wanted, and has certain parameters for the model and the method used inside this sub workflow. Next step is to create a unit that will represent the first part of the logic included in my workflow. So what I do is that I scroll down to the bottom, click on plus unit, and click apply. So now I have created the default pw_scf template to the unit. If I go and navigate into it, click on it to open, I'll see that there are multiple flavors available as part of the selection for this unit. And those include the SCF by default, and then NSCF, bands, relax, and other types of pw.x calculation setups. So for this case, I do not need to change it from the default, so I'm just going to use pw.scf. One moment. And we can also see that there are certain properties that we extract from this calculation. And we have a set of monitors that we also extract during the runtime. So properties are extracted at the end of the calculation, and monitors are extracted at the end of it. If we don't want the properties to be associated with this material permanently, right? If we're just trying to draft the workflow, we can check this draft button, the draft checkbox, and these properties will be present in the job, but they will not be associated with the material inside the database, inside the collection. At the bottom of this dialog, we can see the template, the input template, which contains the Fortran name list for the quantum espresso syntax. Now, as you can see, we do not actually have the final information here about the material, but we have a set of Jinja input variables, right? So we used a templating engine for Python called Jinja, and we pass the material information to it at the time of rendering. So if you go and click on the preview button, which I will demonstrate in a moment, we will see that the material information is populated here. But before we do that, we need to understand how to translate the logic that we have inside the input files into this template. And for that, we need to compare the flags that we have in each of the name lists, which I do now. And I see that some of them are different. So I copy the flags that are present inside my input file into the template. And I do that for each of the name lists. For example, the smearing is different. In this case, the electrons namespace is completely different name list. And I delete the extra name list for ions and cell because we do not have the ionic relaxation here. Okay, now I'm done with transferring the information from input files. I can click on the preview button. Here is the template data that this template will be previewed with. And when I click on the preview button, I can see that the material information is in fact populated. Okay, some of the change variables are still not resolved, and that's because we resolve them during the runtime, the calculation time during the execution of the workflow. It really should not matter for the users where the job is going to be located in the infrastructure, and that's why we keep those variables unsubstituted. Now, the same process I can repeat for the second unit of the workflow. So I click on add another unit, and here we go. It's pw.SCF by default, but then I change it to pw.NSCF to be able to work with non-self-consistent calculation templates. And as you can see, the calculation type is automatically set as NSCF. And then just as with the previous example, I copy the necessary information into each of the Fortran name lists, right? And at the end, I preview this file to make sure that it in fact contains the right information. And that essentially concludes the creation of the workflow. Now, I need to adjust the metadata. I also change the name of this workflow. I add a tag to it to be able to find it easier in the future. And then I click on the save button in the header to save it inside my account collection. So inside the account collection, now I see this workflow with the metadata that I just attached to it. And I can navigate back to it, see how it looks, and adjust it in the future. Okay, so that is how we migrate the information from Quantum Espresso input files to create a material and a workflow. The other option, as we have more and more users joining the platform, is to use the workflows bank, a shared collection of the public workflows, the workflows that users make public. And the likelihood of those workflows that you are interested in to be present in this collection today is relatively high. And we have a set of template workflows coming from the curator's account, the account curated by the platform administrators, so the exabyte team, that contains several dozens of templates by default. So we recommend starting by using those. And there are also a set of workflows that come from other users. All of them are stored inside the workflows bank. So what you can do instead of starting from scratch is to navigate to the bank. So click on the left-hand sidebar, open it, go to bank and workflows, and then search for the desired properties there. So for band structure in this case, select one of the workflows, click copy, and it will be copied to your account collection. So when you navigate back to your account, you'll see that this workflow now is part of your account collection. By default, we initiate the new account with only the default material and default workflow, only one, keep it clean. But it's relatively simple to go and copy the workflows from the bank for the ones that you're interested in. Okay, so now we have a quick Q&A session again. I still see one hand raised. Adaniye. I suggest that we still cover the jobs first to make it clear, and then we can go into discussion at the end of this talk. I do not see any questions in Q&A, so it looks like it might not be urgent. If it is urgent, please ping me either in chat or in Q&A, and we can facilitate the conversation. In the meanwhile, before we get to the Q&A part at the end, let me cover the creation of the jobs. So once we have created the material and the workflow, we can now set up a simulation with this material and workflow information. And for that, we now have two options too. We have an option to use the command line, and that's what we covered previously in one of the earlier webinars. There's also a documentation tutorial that you can follow on your own. Today, I will focus on reusing the material and workflow entities and using the web interface to do simulations. So the first step in creating the simulation is, again, going to the project. Actually, we cannot create the jobs directly from the list of the jobs. We need to navigate into one of the projects. That's how we organize the calculations. Let's go to the default project and click on the plus button to navigate to the job designer. And inside the job designer, you will see 3 tabs corresponding to the material, workflow, and compute information. So what I usually do first is adjust the name of the job to make sure I can find it easier in the future in the list. And then I set up the material and workflow information for this job. Initially, it is populated with the default material, Silicon SEC, as we already know it, and the default workflow that we had for this account. So when I click select materials, I'm presented with a list of materials that are already inside the database. So as we created one earlier, we have this material available for selection. So I do that exactly. I select the material, click select items on the top. And here we go. We have this recently created material inside the job designer session. I repeat the same for the workflow. Select the workflow that we just created. And here we go. We have material and workflow preset for this job. The next step is to inspect the workflow and modify it and adjust it as necessary. We do not allow to change the logic included in the workflow. So you won't be able to add additional units to it for obvious reasons, right? If we designed a certain logic and we've stored it in the database, and then at the point when we create a calculation with this workflow, we completely change the logic. That would be difficult to manage. So instead of changing the logic entirely during the job creation, we would send the user back to the workflow designer if they would like to adjust the logic inside the workflow and change the number of units, for example. But there are certain parameters that we can adjust during the job creation. For example, if I look at the list of the key points used for this calculation, I'll see that we are using the default uniform grid inferred from the KPP array, key points per reciprocal atom, settings that is global to the platform, right? We use 2000 as the KPP array, and that's how we infer the default key grid. Inside the input files, the key point grids are different. And in order to change those, I can use the important settings tab at the top of the sub-workflow window. That's sub-workflow panel. So I click on it and navigate to the corresponding units, pw_SCF and pw_NSCF, and I change the corresponding parameters. So instead of 5x5x5, I have 4x4x2 and 8x8x6. And I reflect in the name that we indeed adjusted the key grid. All right. The third step in this progression is to select the compute parameters. And here, an important parameter is the time limit. And the time limit is the maximum amount of time that we allow this calculation to run for. So if it takes more than an hour, in this case, it will be deleted by the system software. So we have to be careful. We on purpose install this time limit to make sure that users do not overspend on the calculations. We recommend for production calculations in this case, I have a relatively large unit cell for this material. So I recommend using the ordinary regular or ordinary fast queues. And for cluster 001, I recommend selecting 18 cores for the optimum performance within a single calculation node. And then I also select the notification parameters for me to be notified when the job starts, abort it, or when it ends. Okay, and the next step is I click on the save button in the header to save this job. And then I am redirected back to the list of the jobs for this project, and the job is shown in the pre-submitted status. Here we go. Here is the job that we just created. I can open the dropdown for it and click run to submit it for execution. What happens then is that the job is transitioned from the P pre-submitted run status to the submitted status, S, in darker, shown in darker blue. And then within some time, it is transitioned to the active status. So within 2 minutes, the infrastructure for this calculation is provisioned in the cloud. So we ask the cloud providers to set up, on the back end, we ask the cloud provider to bring us additional calculation node. We add it into the cluster, and we start this calculation on it. Then I can navigate into the job. And now, besides the compute, workflow, and materials tabs, I'll also see the results and files. So as the calculations are progressing, the results and files tabs will be populated. We can see now the workflow, sub-workflow, and the corresponding unit are all highlighted in orange, which means that this is the currently active workflow, sub-workflow, and unit correspondingly. When we navigate into the unit, we click on it, we can see the output as it posted back to the web application from the infrastructure components in the real time. So the output is updated as the calculation progresses, and the output also includes things like convergence graphs, so we can see that the calculation in fact is progressing in the right direction. And when the unit is finished, we can see that it is highlighted in green, and the next unit after it is highlighted in orange to understand that it is the active one now. If you look at its output for NSCF, it will take a few minutes for it to complete. It's a production type calculation. And at the end, we'll see that both of these units are now colored green. Okay, so I have executed this job inside the OR queue on 18 cores, and now both of these units have successfully finished. And I can view the results for this job. So if I navigate to the results tab, I can see the results for this pw.NSCF unit. That includes things like the total energies, the Fermi energies, pressures, forces, and so on. And then if I navigate to the files tab, I can see all the files that have been produced inside this calculation. Let me demonstrate it again. So the files are available inside this tab. We can click on them to download them to a local computer, or we can visualize some of them in the web, in the web application. Now, there is an optional step that we can also execute here that sets up our discussion about collaboration. When we exit back to the list of the jobs, we have the option to share this job with another account. I have executed this job under the webinar account, but I would like to also see it when I'm logged in under my personal account as Timur. So what I can do is I can click share and select my name there to be able to share and access this information under that account. So I give myself the read permission to this calculation. And now we can see that this job has been shared. And if I go and navigate back to my personal account, I will be able to see this job as I will demonstrate now in a moment. Okay, so here is a quick summary about the command line versus user interface originated jobs. Command line calculations are quick to start with, but every single time we are required to modify the input file every single time the job is created. And that usually includes modifying the materials information as well as the computational parameters. And we only store the data on disk. It's not stored in database by default, and it's difficult to collaborate and work on these calculations collaboratively. Now, the jobs that we create on the user interface take time to get used to, but it can help us deal with multiple materials at the same time. We can organize data in database automatically, and they enable collaboration. So multiple users can see this information, multiple users can see this information as it's being produced in the real time, and they can exchange comments and understand what went wrong in case the calculations don't proceed as the way that you expect them. Most of the people use a limited number of workflows, according to our experience, usually probably half a dozen or within a dozen or so. So when we have created those workflows that people use on a daily basis, the little modifications are required. And that's the beauty, that's the usability and accessibility of these types of calculations, as it can be improved inside the Exabyte platform. Now, let's talk briefly about the sharing and collaboration framework that we deploy. First of all, we can navigate to multiple accounts. As being the platform users, I have multiple accounts that I can use the platform under. It's always a single personal account that I belong to. That's just identifying myself. And then multiple organizational accounts that I can work with the platform under. So here I am logged in by default as Timur, as my personal identifier. Then I click on the right-hand sidebar, my accounts, and then click on the seminar account to change and see the items that this account have created inside the platform. So if I go to the materials tab, I will see the materials that belong to this account. And so on and so forth for all the other entities. Now, when I navigate back to my accounts and switch back to my personal account, accordingly, the list of materials is different, right? So that's how we can change between organizational account and personal account using my account switcher. For organizational accounts, we have a way to set up permissions, role-based permissions. And role-based permissions are based on the team management. So here is an example account page. We can navigate to the people to invite people into this account as members by selecting them inside the list and clicking select items at the top. So now this account has 4 members. One of them is an administrator and owner, as you can see. The others are regular members. So to give these members permissions to see and create new materials, we need to create a team first and then associate the entities with this team. And this team can have multiple different permissions associated with it. So this team can grant multiple different kinds of permissions. I'm selecting read and edit for this particular team. Actually, not just read. So this team will be a read-only permissions team. And then I need to add some of the users that are just some of the members of the current account to this team. So I select them back here. And now these users are part of this team. The next step is to select the entities that this team will be granting access to. So I select the material that these users will be able to access. The account members will be able to access the Silicon FCC material. And the same I can repeat for workflows and jobs. Right? So I need to identify the entities that this team will be giving access to for the team members. Now, besides the permissions, we also have certain levels of access to each of the entities that we create. And here we have an example. We have a set of jobs that can have different access levels for each of them, right? Either it could be a job shared with another account, a job shared with all other accounts in the platform. shared with anyone that has the link to it, and shared with anyone who has who is even going to search for this job on the web. Right? It's indexable by Google and other search engines. So let me show you how we can share a job with another account. We select it in the list, click on the share tool in the list of tools at the top, and then select the account and click on the permission. So I give the webinar account read permissions to the job. Now, equivalently, we can share another job with all the accounts present in the platform by selecting public as the account that we share this job with. It's a system level account that will give access to all the other accounts present in the platform. And equivalently, we can share the job with anyone that has a link by selecting anyone with a link, and share the job anyone on the web by selecting the corresponding option. Now you can see the permissions matrix, the access levels matrix for each of these jobs reflecting the corresponding permissions, the corresponding access levels. To be able to see the jobs that we have shared, we need to navigate into either Shared With Me tab in the left-hand sidebar, or into the Shared Publicly view. And here I'm highlighting the two in the left-hand sidebar and the corresponding access level matrix permissions here. So the shared flag corresponds to the jobs or entities that are shared with me, and the public flag corresponds to the jobs or entities that are shared publicly. There is a concept of the owner and creator for each of the entity. So for example, now I'm under the webinar account, but I can see the job that was created and it is owned by Timur because I have explicitly given webinar account the permission to see this job. And now it appears under the Jobs tab inside the Shared With Me dialog for this account. All right. So once again, here is how we share an entity from one account to another. We select the entity in the list and then select the account and give it the read permission. And we can see the corresponding access levels matrix in the list. So here is how the Shared With Me dialog looks like for a personal account. This is the job that I just shared earlier in the previous section between the seminar account into my personal account. So if I navigate into Shared With Me and click on the jobs, I will be able to see this entry there. And I can navigate further into the job and view its results. The sharing is also enabled by default for the new accounts, for the accounts that are on the free service levels. And here is how we can see the publicly shared entries in the platform. We need to navigate into Shared Publicly using the left-hand sidebar. And we can go into the list of jobs, for example, and there are going to be quite a few. So we would suggest changing the number of jobs visible to 50 per page, at least. And here is what the list looked like back in April of this year. So these jobs are created as the users access and utilize our platform to create and run those jobs. We can see what happens to the platform. It's like the large activity list within what's happening in the platform right now. Now, the final point I wanted to mention is that there is a way to attach a description to the entities that we share. And that's a way for us to exchange notes, to speak and put thoughts about the entities and share them between different users. How we would go about this is we would navigate into the entity viewer, right? So the entity we'll open one of the entities, the job in this case, and we'll click on this information icon to add a description to it. We can use Markdown language to form this description and add things like headers or links or even source code if necessary. And this is how we can add an explanation to this job. And then the explanation will be visible when we enable the corresponding column by using this drop down in the list of the jobs. Right, so when we enable this column, ID and description, we will be able to see the description in the plain text. And then when we navigate back to this entry, we'll be able to see it in the Markdown, in the properly formatted HTML Markdown format. Okay, so that's how we exchange information between multiple users. And the last part here that I mentioned early in this presentation is the last concept that we use to facilitate the collaboration is the entity bank. By default, as I mentioned, each account has a default material, which is Silicon FCC. And naturally, this would lead to a lot of duplication. So what we enable is a way to map equivalent materials into unique entries inside the materials bank. So for each entry in the materials, there is a corresponding entry in the materials bank, which is unique. Materials are not unique, materials bank items are. And when the account has private access, private data access scenario enabled, then no other account can access the entry inside the materials bank, but the original creator. And when this option is not enabled, other accounts can see and access the entries that are being created under the materials and materials bank by the account which has the public access. All right, so that's a way for us to facilitate sharing in a secure and private manner, and at the same time keep track of the unique entries inside the materials and workflows database. So let me summarize here about the accounts and sharing. Entities can be shared within one account for organizational account or between multiple accounts. Account teams have different permission schemes and allow account members to perform different actions on the account entities according to these permissions. Sharing between individual accounts is also possible, and sharing with all platform accounts and external non-registered platform users is another option. Entities that support metadata description include materials and jobs and workflows as well, so that users can exchange information about how they have created these entities and put comments. And unique entities are consolidated inside entity banks to be able to track unique entries and to accumulate the knowledge base per each account and globally within the platform. All right, so now I think I'm done with most of the content. We can go and answer any questions as you might have. I do not see the questions inside the Q&A. Adania, would you like to speak up and ask the question that you had before? You raised the hand. Please raise a hand if you still have a question. I don't hear back from Adania. Looks like it may have been just an accident. Raised hand was just an accident. If that's the case and there are no more questions, then I'd like to thank you for your participation. This presentation will be sent to you by email. You'll be able to access the PDF copy of it, and we'll also upload the video online so you can follow the presentation and execute some of these actions in the platform. Next seminar. Yeah, there is a question from Adania. Can I have access to the introduction to this by email later? Absolutely. All the seminar participants, as your registered participants, will receive in 24 hours a follow-up email that includes links to the PDF and the YouTube video that explains, that records our current communication. So you will be able to follow it on your own. If you still have any other questions, please feel free to email me directly at timur@exabyte.io. Or if you face any problems with the platform and its operations, you're welcome to submit a support widget, support ticket through support widget. Our team usually replies pretty quickly within a couple of hours. All right. If no other questions, I would like to thank you once again. Have a good rest of your day, and we'll speak with you again next month about getting started with the exabyte platform. This will be our next communication in about 2 to 3 weeks. Thanks, everybody. Have a good day, and see you next time.